Okay, good. So, welcome to today's class. Of course, we are going now to start a new topic. And before then, I want that is to illustrate. Okay, I usually love that is um, like doing an overview, okay, of a class before now we can go to the like we can deep dive, okay, about what we've discussed. Okay, so basically here we are going to talk about regression analysis. regression Analysis. Under regression analysis, we are going to discuss about deeply discuss about linear regression. Okay, and also we shall state and show like give an illustration on multiple linear regression. So this is simple linear regression and multiple linear regression. Okay, so basically uh, what is regression? Okay, and how do we do regression? So let me start with a basic model, a very basic model. So maybe can someone remind me uh, what, or maybe can someone remind me the equation of straight line? I know this is something we learned back in our high school. Okay. Yes, Maureen.
Hi, good evening.
Yes, good evening.
The equation of a straight line. One of the ways to get it is y equals to mx plus c, where m is the gradient of the line and c is the y-intercept.
Correct. That's very correct. So, if you can remember, this was the equation of straight line. Okay. Now, this equation of straight line, okay, we can use it as a model. Okay, we can use it as a model. All right, I will also show you that is during our practicals how we can use the equation of line to make a model. Okay, and how we can use that model to do what? To do some prediction. Okay, so basically this is the equation of what? Of the straight line. Okay, maybe representing it in a graphical, let's say on a graphical manner. I'm assuming this is a what? This is a straight line. Okay, okay, like most of the what? Most of the points are cutting along what? Along the straight line. Okay, okay, good. Now this, let me just show you. So this is our equation of straight line, that is mx plus what? Plus c. Okay, this is just a refresher of what we learned. So we've seen that m is the gradient or is the slope. Let's assume maybe like this point. Okay, we have this point, one point, as what? As let's say 20, and we have another point here as what? As 10. Of course, we have 15, we have 5. This is just an illustration. It can be a perfect plot. Okay? All right. So, we add, that is a way of calculating what? Slope. If you remember, slope was, that is the slope was calculated by change in what? In y divided by change in x, meaning the difference that is between the between vertical distance between two data points. Like for example, if I can say we have at this point we have, let's say 15, and at this point maybe we have what? We have 20. Okay, just a minute, I let someone in. Okay, so basically we know that now our gradient will be change in y. So change in y, this will be our change in y, and this will be what? Change in what? Change in x. That is the distance between this point and this point will be change in what? In x, because it is along x-axis. Okay, then here between this point and this point it will be change in what? In y. Why? Because it's a vertical change along the y-axis. So basically calculating this value, we'll say now our slope, okay, which is our m value, okay, will be given by, so change in y, that is 20 minus 10, so it will be 20 minus 10, okay, divide by change in what? Change in x, that will be 20 minus what? 5, so it will be 15, sorry, 20 minus 15. So in this case it will be 10 divided by what? 10 divided by 5, and of course now our gradient will be what? Will be 2. So if we were to do what? If we were to insert or use now this gradient, then our new equation would be equal to, that is y is equal to 2x plus c. Okay, why? Because we've already calculated for the gradient. Okay, then for that is for the c, as Maureen said, it was what? It was the y-intercept. Okay, so for example, when we extrapolate this line, it will cut the y-axis at some point. Okay, now that is that point where the that is our line of best fit, or the our regression line cuts the y-axis. It is what? It is the y-intercept, and that's the value of what? Of our c. Okay, so let's assume it cuts the that is the y-axis at 2.5. Okay, so now our new equation of that is the equation of the straight line will be 2x plus what? Plus 2.5. Why plus? Because it has cut that is the y-axis on the what? On the positive side. But if the line was like this, okay, if the line was like this, okay, then definitely we know this will be the negative y. So it will cut the y-axis at what? At a negative on the negative side. So in this case, it will change from positive to what? To negative. Okay. So basically, this how we that is we dealt with what? With the equation of straight line. Okay. Good. Still on the equation of straight line, we add m, okay, x plus what? C. Now, when it comes to regression, we have different names of what? Of these variables. Okay, variable m, variable y. Okay, sorry, yes, this is a constant, sorry, not a variable. So we have name for variable x, we have this constant, then we also have a name for this constant, and we have also this that is this constant. Okay, so basically in terms of regression language, what name is given to this variable x? Someone? Someone? In terms of regression, yes, is it?
Independent variable.
Sorry, so that is the x is the independent variable.
Mm.
Okay, or We also call it predictor variable. Predictor variable. Predictor predictor variable. Why? Because it is the value which it's being used to predict what? Our output, which is our y. Okay? Then we have y. We usually call y as what? Dependent variable. We usually call y as a dependent variable. Why? Because it depends on this variable and some constants, okay, to get the value of what? To get the value of y. So that's why we usually call it dependent variable, okay? All right. So in this case, we have dependent variable, dependent variable, independent variable, and then we have the constant attached to x variable. Okay, we have this is the constant attached to the that is to the x variable. In other words, it is the slope. Okay, then c it's that is the other constant which is we've called y-intercept. Okay. All right. Let's assume we had two variables, that is rainfall amount, and we also add umbrella cells. Okay, good. We can create a model, okay? We can create a model that will what? That will help us in future to predict maybe the umbrella cells or maybe the umbrellas we might sell, okay? Given a certain amount of what? Given a certain amount of rainfall, okay? So in this case, we might say y, okay? Or we can say umbrella cells. We can write the model as umbrella, just a minute, umbrella cells, umbrella, that is dot cells, will be given by, okay, we have a constant, we can call this constant maybe a, okay, we can call this constant as a, multiplied by, okay, amount of rainfall, that is of amount of of rainfall. Why am I saying that? Because definitely here, with if we are forecasting the umbrella cells, then what do we need for us to determine the cells of umbrellas? Okay, so it meaning our rainfall or the rainfall data will be what? Will be our independent variable. Okay, our predictor variable. We are using rainfall amount to predict what? The umbrella cells. That's why I'm saying now, in this case, our model will be umbrella cells will be equal to a constant A, okay, multiplied by, okay, amount of rainfall in millimeters, okay, plus or minus, okay, I'll say plus or minus what? A constant, another constant, let's say b. Okay, I will have another constant. So basically you can see this is a model. Okay, this is a predictive model given what? Given different variables. Okay, and the model it's taking the what? That is the linear equation y is equals to m x plus what? Plus c. Because you can see from the that is from the model, we have umbrella cells will take the place of what? Of y, because this is our output. We are expecting to know maybe the umbrella cells which we can sell, okay, given a certain amount of what? Amount of rainfall, okay. And then we have a as our slope, okay. Slope meaning this is our gradient, okay. Then we have amount of rainfall as our independent variable, okay. And then we have b as our y-intercept. So basically This model takes the what? The equation of that is the linear equation. Okay. Yes, or equation of a straight line or a linear equation. This is also an example of linear equation. Okay. The same thing. Let's assume we want to do what? We want to predict. Okay. That is the amount of salary. Okay, or yes, or maybe the salary to be paid given what? Given number of years in terms of experience. We are looking at salary being influenced by what? By experience. Okay, so in this case, we might say now salary will be determined by a constant, let's say theta naught, okay, multiply by now experience in what? Experience in years, okay, plus maybe theta 1 as another constant, all as what? As our that is as our y-intercept. Okay, so basically what we mean here is our what? The years of experience will do what? Will determine the salary, given of course that is historical data. In this case, you must have historical data for us to predict about the future, that is about maybe the next step or the next year or the next salary. So of course we must have historical data when we are dealing with what? With linear or with regression analysis. Okay, are we good up to that point? All good? Okay, right. Maybe the last thing, this is an example of simple linear regression. Okay, for multiple linear regression, just to keep just as heads up, for that is for multiple linear equation, the difference is that for simple linear regression we only have one independent variable, okay, but for multiple linear that is a linear regression, okay, we have what? We have more than one independent variable. So in this case, you might find we have an equation like this, that is a that is maybe y is equals to a multiplied by x1 plus b multiplied by x2 plus what? Plus c. Basically meaning A and B, it's what? They are constants, and C as well. Here we also include now an error term. Okay, that is the error term or the epsilon. It is the what? It is the y deviation. We shall see that. Okay, so y is equals to that is our first constant multiplied by our first independent variable. So our point of focus is what? It's on the number of independent variables. So if we have more than one independent variable in uh, your regression, okay, then that becomes what? A multiple linear regression. Okay, if you have one independent variable in your regression analysis, then that becomes what? That becomes a simple linear regression. Good. Now let's go to the notes. Okay, we'll discuss because we also have some assumptions which we usually that is usually odd. Okay, we have some assumptions which we usually assume. Like for example, if we are trying to check the regression between that is y and x, we usually say there must be a what? A linear relationship between y and x. Okay, if we don't have that is a linear relationship, that now becomes a non-linear regression, like for example logistic regression. Okay, another assumption maybe we usually say when in case of multiple linear regression, okay, we should not have high correlation between what, between the independent variables. Okay, and also but we shall check on that. Also the error terms should what, or must approach like a normal distribution. Okay, yes, so but we shall check on that as we move on with the class. Okay, good. So, what is linear regression? That's where we have to start. Okay, so linear regression analysis is used to predict the value of a variable based on a value of another variable. Okay, the variable you want to predict is called the dependent variable. Okay, the value, okay, sorry, the variable you want to predict is the what? Is the dependent variable, as I have shown you. Like, let's say example of y is equals to mx plus c. This is always our output or our objective. We want to get this value. So this value is the one which is called dependent variable. Okay, it is called dependent variable, and it's the one which we are trying to predict. Okay, so the variable you are using to predict the other variables are called independent variable, or it's called a dependent variable. So basically, um, this is that is our x, because we are using x, that is input x, okay, to get what? To get y. Because we are assuming if you are given that is historical data, you must have granted and y-intercept. Okay, so maybe what we are lacking is what? Is the x value or the independent variable. Okay, so this now it's known as the independent variable. Okay, why? Because we are using it to that is to determine or to predict what? The output, which is our y. Okay, good. So this form of analysis estimates the coefficients of linear equation involving one or more independent variable that best predict the value of dependent variable. Okay, so linear regression fits a straight line or a surface that minimizes the discrepancies between the predicted and the actual output values. Okay, there there are simple linear regression calculators that use least square methods to discover the best fit line for a set of paired data. But for us, we are going to use Excel, okay, to determine all this. Okay, we are going to use Excel to determine that is the equation or the line of best fit. Okay, to determine the line of best fit. A minute, I had someone else. Okay, good. Let's continue. Um, maybe like a task maybe for all in an illustration for linear regression is that linear regression performs the task to predict a dependent variable y, as I had illustrated, based on a given independent variable x. So our independent variable is x, our dependent variable is what? It is y. Okay, hence the name. So these regression techniques finds out a linear relationship between the y, that is the x's, which are the inputs, and the y, which is the output. So hence now the name comes in as what? As linear regression. Why? Because we are trying to find out a linear relationship between the two variables. Okay, that is the input and the output. Okay, so in the figure above, okay, or in this figure, you can see X input is what? Is work experience. If we take the example I have given you on that is coming up with a model that will predict what? Will predict maybe the amount of salary given work experience. Okay, so in this case, in this figure, work experience, we have it as our input or our independent variable, that is X, and Y is the salary of person. Okay, so why it is the salary of the person, or basically what we are trying to predict, because here our model wants to predict maybe the amount of salary given a number that is a number of years of experience. Okay, all right. The regression line is the best fit line for our model. Okay, the regression line is the best fit line for what? For our model. So of course, if we build that model, we'll have this model, that is salary is equal to that is our our constant, which is the slope, multiplied by experience, the number of years of experience, okay, as our independent variable, plus the other what? The other constant, which is what? Which is our um, which is our y-intercept. Okay, all right, good. Let's continue. So, of course, when we are talking about regression analysis, we usually formulate an hypothesis, okay? Or basically, here the hypothesis is our assumption. That is, our salary will be predicted by our model. That is, salary will be equal to our constant multiplied by our number of that is years in terms of experience, plus the constant. Okay, so basically this is our hypothesis. We are assuming this is what? This is our model, and our work is to determine, is this model that is viable, or does this model qualify to be used. Okay, now depending with what? With measures we usually use to do what? To examine if our model, it's a good model. Okay, for linear regression, simple linear regression, we will use what we call that is coefficient of determination. Okay, so the coefficient of determination value, it is the one which will show us if this model, it's a good model. Okay, because it will show us how our data is fitted in what? In our regression line. Okay, and of course we have other ways of optimizing the model. We shall also check on that. And we have like mean squared error. It's one of the cost function, or it's one of the optimizer for simple linear regression. Okay, and others, you other measures, uh, you will learn them during that is during our what? During your machine learning class, where you will be also able to calculate the accuracy of your model. Okay, yeah, so that's something which will come later. So for hypothesis, we have x. Okay, so x, basically they are our inputs data. When you'll be discussing about machine learning, you'll term x as what? as training data. Okay, you will talk about training data, okay, and testing data. Why? Because it's out of the inputs, okay, data, where you will do what, where you will divide now the data, maybe using a rule of 80-20, 80-20 rule, to do what, to determine the what amount of data to use to build the model, and what the data you will use to test the model. Like for example, a model maybe to predict if a certain that is picture is of a cat or is of a dog. Okay, so definitely you'll have that is different pictures of dogs, different pictures of what, of cats, with different species, all those. Okay, and then you'll use maybe 80% of that data to train the model or to create the model. Okay, and then after creating the model, now you will have some different or 20% of your data, you'll use it to test the model. Okay, to see if maybe I upload that is a cat picture. Okay, is our model able to what, to tell us this is what, this is a cat or this is a dog. Okay, so basically that's a linear regression, or simple linear regression is one uh, of the simplest supervised machine learnings. Okay, because if you are to create a machine learning algorithm to predict, maybe all to classify, okay, a dog and a cat, okay, that will be under that is the simple supervised machine learning. And also for linear regression in terms of predicting, okay, if you create a predictive model, definitely you will also talk about linear regression as a supervised machine learning. Okay, all right. Then, when training the model, it fits the baseline to predict the value of y for a given value of x. Okay, the model gets the best regression fit line by finding the values or the coefficients. Okay, that is the coefficients here we have theta 1 as our y-intercept. Okay, then theta 2 as the coefficient of x, or it is a constant to variable x. Okay, all right. So that's about maybe the introductory part. Maybe to check types of linear regression. Okay, so we have two major types of linear regressions. Okay, but we have different types of regression. Here we are only talking about linear regression, meaning there is a linear relationship between what? Between your variables. Okay. But when we are talking about regression, types of regressions, we have linear regression, we have logistic regression, we have another almost, we usually have around four types of regressions. Okay. All right. So for the simple linear regression, yes, I had already illustrated this. So if a single independent variable is used to predict the value of a numerical dependent variable, then such regression algorithm is known as simple linear regression. Okay, like for example, as we had said, that is y is equals to mx plus what? Plus c. We only have one independent variable. Okay, so basically this is an example of what? Simple linear regression. Okay, and the one with more than one independent variables, okay, now becomes what? Now becomes uh, the multiple linear regression. Okay, all right. So if a single independent variable is used to predict the value of numerical dependent variable, then such linear regression algorithm is simple linear regression. Why? Because we are only using one independent variable to determine or to predict one dependent variable. Okay. When we are talking about multiple linear regression, here we are talking more than one independent variable used to predict what? The value of a numerical dependent variable. Okay, so that in that case, we'll talk about multiple linear regression. Okay, good. Let's go to the linear regression line. Okay, so definitely for regression line, we might have two regression lines. Okay, either a positive linear regression line or a negative linear regression line. Okay, like for example, let me illustrate that. Okay, let me illustrate that. So let's assume we have this graph. Okay, and also we are having this graph. Sorry, let me redraw it. Okay, so this is y, this is x, this is x, this is what? Y. So basically from the first, this is the positive, it's the positive regression line. Why am I saying it's positive? Because as x increases, okay, you can see as x increases, so does the what? So does the y. Okay, so you can see as what as x is increasing, the value of y is also increasing. Just let me just take an example. Maybe at this point, okay, let's take y value at this point, okay, and y value at this point. So let's assume this is 10, let's assume this is 20, let's assume this is 5 and this is 10. Okay, so you can see as we are increasing the x value from 10 to 20, the y value is also increasing from 5 to what? To 10. Why? Because you can see here we have a value of 5. The y, that is our y here, it's 5. And when we increase the x, okay, our value of y will also increase. So in this case, or for a case of positive linear regression, okay, line, we'll say that as one variable is increasing, okay, the other variable is also increasing. Okay, what about for the case of negative linear regression line? Okay, so in this case, you will see that as the value of x increases, the value of what? The value of y, it is what? It is decreasing. Okay, let's take maybe the example of y value, that is the y value at x value of 10. Let's assume here it's 20. Okay, and then maybe increase the value of x to 20. So definitely you can see the value of what? Of y will go down. Okay, so in case of this kind of relationship, like whenever one variable is increasing while the other one is decreasing, then we'll have what? We'll have a negative regression what? Regression line. Okay, good. So let's try and see what the notes are telling us. Okay, so for linear regression line, a linear line showing the relationship between the dependent and independent variable is called a regression line. Okay, and we have two types of regression line. Positive linear relation, that of one shows positive linear relationship. Okay, so if the independent variable increases on the y-axis and independent variable increases on x-axis, then such relationship is termed as what? A positive linear relationship. Like the both variables are increasing. Okay, these two variables are doing what? Are increasing. Okay, what about the negative linear relationship? Okay, so for the negative linear relationship, as we had said, if the dependent variable decreases on the y-axis, okay, and independent variable increases. So you can see one is decreasing and the other one is increasing. So the of course the what? The relationship there will be what? It will be a negative relationship. Okay? It will be a negative linear relationship. Any question up to that point? Because I want to do now the last slide and maybe we will close that for today. Okay. So that now next week, Monday, we may talk about how can we optimize the this model. Okay, how can we optimize the model? Okay, and then we'll do after seeing that is after discussing that, we'll also come to model performance and then assumptions of what? Of the linear regression, and then we'll jump now direct to what? To the practicals. Okay, can see Milas has raised hand. Yes, please.
Good evening.
Good evening.
Okay. I have two or three questions. The
Okay.
first one, you're talking about the linear relationship, the linear regression.
Uh-huh.
And I think for the linear regression to to do the linear regression model, there should be the relationship of the linear relationship between two variables.
Yes.
And if there is no linear relationship, maybe there will not, your predictions will be wrong.
Yes, correct.
And I'm wondering what is the metric that we will use in order to know whether there is a linear relationship between two variables for us to use the linear regression model to do our prediction. Is
Okay.
it a correlation? Is it a different metric?
You have, in fact, you have the answer. Like you can perform, first of all, you can perform correlation. Okay, you can try to compute the correlation coefficient to see if there exists a linear regression between what? Between these two variables. Okay, you can try and get and see that. If you get a value which is greater than 0 0.5, okay, then it means there will be some linear relationship, okay, between those two variables. But if you get a value which is less than it's moving to, it's close to zero, then in that case there might be a no or less linear relationship between the two variables. That's the first approach. The second approach, maybe you can try to plot a graph, okay, of those two variables and see if you will get like a kind of straight line. Okay, if you get a kind of a straight line, okay, that is between these two variables, then it will be possible to do what? To conclude that there is a linear relationship. But if you are getting something like a curve, then that means it's not a what? We don't have a linear relationship in between those two variables. Yes, I hope the first question is answered. Maybe the second question.
Yes, it is answered. So now for multiple linear regression model,
Mhm,
we we use more than one independent variables.
mhm,
Some can be can have a linear relationship with the dependent variable, while some do not. We leave out those who don't have the linear relationship with the independent variable. What will happen?
no. So, maybe let me answer that. So, for multiple linear regression, it is not a must for all those independent variables to have like a linear relationship with what? With the independent variable. As we'll be checking, as we'll be checking through the that is the assumptions. One of the assumption is the assumption of multicollinearity. Like we should not have that is high correlation between the independent variables. Why? Because if we have high correlation between the independent variables themselves, then it will be difficult for us to know which independent variable is affecting our output. Okay, so in that case, we will have that is the independent variables. It's not a must to have that is a high correlation. Okay, between what? Between themselves, provided like if you check on the individual independent variables, we have some correlation between the each individual independent variable with what? With our output. Okay, like for example, in our data set for income, expenses, number of family, okay, and maybe the earning, okay, the number of earning people in that family. Okay, in that case you can see we have more. Those are, we can use those as what? As different that is variables, okay, to determine, okay, or to predict what? The expenses maybe which will incur in future. Okay, so in that case, each, you can see each as what? Each as a little or as a correlation between what? Between themselves and what? And the independent variable. Taking expense as the independent variable. Of course, the number of people earning in a family might influence what? The expenses we are using. Okay, also maybe the number of people who are earning in that house, okay, it might also influence what? Our expenses, but very minimal influence. Okay, so with that case you can see we have like kind of relationship between the independent variables and the dependent variables. I don't know if that was clear.
I'm not sure, but I have got a little bit about the idea,
Yes, but
which
maybe I
means
will
that
explain that much
when
more.
we even when we find that there are some that are not that have a correlation between the independent variable and dependent variable above 0.85, we proceed with our development of the model.
Yes. So maybe with that, but with that, we'll also discuss it when we'll be discussing that is between on this topic. Yes, this when we'll be discussing about this multicollinearity. We'll elaborate more on the same.
Okay, good. Let us leave it for this time.
Yeah, okay. Another question? Yes, Elizabeth?
Maybe a clarification, because I think I was breaking on my side in the internet. You said the linear regression models will be using Excel. There's something you said about that, and then the others I don't know what we'll use. Kindly, maybe you
So
could
for
repeat
for
that.
for simple linear regression, we'll use Excel, but for logistic and multiple linear regression, you'll discuss them in depth. That is on machine learning topic. That's where now you'll do it practically through coding. Okay, but for simple linear regression, we are going to perform it using Excel. Okay. Good. Yes, Daniel.
Um, do you have like a formula representing the logistical regression, maybe?
Like a function,
Yes,
or maybe like a formula for that is
like
logistic.
I mean a function like we had where we had for multiple linear we had y like a x1 plus b x2 plus c and maybe an error. That's for multiple. Do you have a function maybe for logistical?
Oh yes, yes, yes. We have a formula for logistic regression as well. We have it. We have it. So maybe you want me to show that. I can just write for you the formula. Uh, Someone has raised their hands. Okay, yes, Elizabeth.
Okay, on my second question.
Hmm.
Okay, wait, just escaped my mind. What was I asking? Give Sorry, I've remembered. So there's this Mela Sedasa question in terms of knowing whether to proceed with maybe let's say a linear regression model. So in real life,
Hmm.
what is expected is if you have variables, if you have a data set with different variables, you have to conduct either the correlation to determine the strength of the relationship before you go ahead. Is that the norm?
Yes, it can, but it depends maybe with the experience you have in terms of dealing with model. Because like for me, I can just see the data and see if it has any linear relationship at any point. Okay, depending on how the values are looking like and how maybe any that is any relationship that might be between between these two variables. Okay, like for example, for the income, if I see if I see we have the income and we have the expenses. Okay, the way the expenses are behaving when income is increased, with that now it can tell me these they are either moving in the same direction or in the opposite direction. Okay, yes, so with that I can really know if we have if we have a linear relationship between between those two variables. Okay, but for your case, if you want maybe to do that before any analysis, you can always also perform linear that is a correlation. Okay, you can always perform correlation to see um, if there exists any linear relationship between these two that is variables. Okay.
Are we checking the covariance? In that case, is it covariance, the directional one, or is it just a normal relation, the correlation?
Correlation.
Okay.
Correlation.
But how can you tell the strength if you have not done? Because you said,
So
I
if
think
you do a
either
correlation, you see the correlation is very simple to do. So if you get that one value, you'll be able to get to know if we have that is a linear relationship. If you get a value which is around zero, definitely you'll that will be a red flag. It's either we have a very small linear relationship between those two variables, or we have no linear relationship at all. But if you get a value which is greater than zero 0.5, then you can see for sure we have what? We have a linear relationship. Even though, okay, even though it might be not that strong, but we have what? A linear relationship. Okay. In terms of direction, if you get a positive or negative value, now it's when you will know that your linear regression line will come to be a positive that is a regression line, or it will be a negative linear regression line. So those are some insights when which you can get even before you can perform the what? The linear regression. I don't know if that is clear, Elizabeth.
yes, yes. Thank you. Thank you.
Okay. We had, is it Daniel? Daniel. So Daniel, you had asked about the function. So like the function for that is is it logistic regression is usually exponent, okay, of, let's say, if it's like, even you can convert, you in fact, let me tell you, you can even convert a linear regression to a logistic regression. Okay, so like for example, let's assume we have a linear that is a linear what? A linear regression. So let's assume we have y is plus, is, sorry, not y, sorry, m mx plus c. Okay, so in this case, the logistic regression equation, okay, is always presented as um, exponent of mx plus c divide by 1 plus this one, exponent of mx plus c. When maybe you are dealing, when you'll be dealing with a logistic regression, you'll come to also talk about something we call sigma. Okay, that is sigma function, sigmod function. But for this one, that is the lecture, that is the tutor will give you more elaboration about the whole function. But this is generally the function which is used for logistic regression. Okay, all right. Another question? Yes, aim.
I would like to say if we are looking at the logistic regression equation that you have already written over there,
Mm-hmm.
I could see that in logistic regression we are trying to go from any value that may be assigned to y or computed to y to be limited between 0 and 1.
Correct.
In that case, if you look at the format of your function,
Mm-hmm.
there could be probabilities that some of the value may go beyond 1 or 0.
Not
So it's
really.
better that
Not really.
it
Uh-huh.
can be 1 over
Yes, that's another way, another way of doing it. It's just because I've not simplified this
Okay, okay.
this equation. You
Yeah,
can
okay.
see if I want now to simplify it, at some point this will like this is not the simplified form of it. Okay, but otherwise, whenever you have an exponent, it's not easy to get a value which is greater than what? Greater than 1. You can even try it on your side.
Okay, with minus, okay. Now, my second question now.
Mm-hmm,
Uh, let's go back to the multiple linear regression,
mm-hmm,
whereby I have a function
mm-hmm,
that maybe f of x, x1, comma, x2,
mm-hmm.
x3
Uh-huh,
is equal a1 times x1 plus a2 times x2
mm-hmm,
plus a3 times x3
mm-hmm,
plus a constant c.
mm-hmm.
Some of the variables may have a negative correlation,
Mm-hmm.
others may have a
Positive.
positive correlation.
Uh-huh.
Therefore, how should I measure the success of my equation after determining its prediction function?
So like to get to know to like to measure the performance of your equation, if it might be a good model, right? That's what we are asking.
Sure, sure.
So don't worry about that. It's still early because we've not reached the point of measuring, because we'll also come and talk about coefficient of determination. Okay, like if I get this kind of that is value, okay, of coefficient of determination, what can I conclude? Okay, how can I infer about my model? Okay, so basically that the value which you'll get at the end on coefficient of determination, which is the function which is used to determine the goodness of the goodness of your model. Okay, will come to what? To determine from that value. We still have a long way to come to inferences, because we've not even talked about that is the R squared. Okay, like this it's coming. It is, let me just show you. You can see how we can measure the model performance, okay, and also how we can optimize. So this is something which we are coming to work with. You can see we have coefficient of multiple determination, which will be now the indicator, okay, to show us if that is the model, it's good, or we will have to change that is the independent variables which we've chosen. Okay, that's okay, aim. Yes, we are coming to that. Okay, I guess we are all good.